So here are some like generic kind of outlines for hints for verifying trigonometric identities. In general, I recommend that people always think about the algebra because algebra rules every branch of math. Sure, we're learning some new things in trig, but the algebra is still there. So it's important to look for the algebra. So some hints here. You want to think about the algebra necessary to perform to get yourself from one side to the other side of the equation. You're going to perform any factoring or indicated algebraic operations. You may have to use some identities, especially the fundamental identities. We use those ones the most. I recommend you always start with the more complicated side of the equation.
Allison, the screen isn't showing.
Oh, shoot. Look at me talking. Thanks, I didn't hit screen share.
Thanks.
There we go. There we go. All right. You want to start with the more complicated side of the equation, and a lot of times that's going to be the more complicated argument. If you have one side that has just theta and the other side has like 2 theta, you want to start with the 2 theta side. It can be helpful to express all trigonometric functions in the equation in terms of sine and cosine and then simplify the result. As you select your substitutions, you want to keep in mind the side that you're not changing because that represents your goal. And if an expression contains like 1 plus sine, multiplying both the numerator and the denominator by the conjugate, 1 minus sine would give you 1 minus sine squared, which you could replace with cosine squared. So that's just a variation of our Pythagorean identity. So I'm going to talk through the algebra. I'm going to do like some side work, and then we'll not write out a nice fluid proof. They are going to increase in difficulty. So these first ones, even though I'm going to kind of talk through it long, you might say, well, I see it right away. Great. I'm just trying to kind of train the thought process so when we get to the more complicated ones, we're already in the habit of doing that. So we want to verify that tangent alpha divided by secant of alpha is equal to sine. Algebraically, notice that we're going from a fraction to not a fraction. Identifying the more complicated side, I'd say that's the left side because the argument is just alpha for all of them, so that's a tie, and a fraction is more complicated than not a fraction. So to go from our left side to our right side, to go from a fraction to not a fraction, that means that something has to cancel out. We need to be able to simplify the fraction. So that's kind of our plan here going into this. We want to simplify the fraction on the left-hand side, and then we should end up with something that is not a fraction. Let's begin left-hand side, and this is just my abbreviation for left-hand side. You could write out tangent over secant if you wanted to, but left-hand side is usually much shorter than what's actually on the left-hand side. Well, tangent and secant right now, nothing cancels out, but we could rewrite both of those trig functions in terms of sine and cosine. So we'll do that. Tangent is sine over cosine. And then secant is 1 over cosine. And when we're verifying these identities, we typically write it in a vertical format. So please don't have your next equals going to the right side. We want to see it vertical. Notice that we have 2 fractions divided by each other. We know that we can turn that division into multiplication by multiplying by the reciprocal of the second one. So this becomes sine over cosine times our reciprocal, cosine over 1. And now we can cancel our cosines. That leaves us with just sine, which is our right-hand side. And then we're done. We verified that the left-hand side is equal to the right-hand side. When we're at the end of writing a proof, we like to indicate that we're done. There's two options. You can either make a little rectangular box and draw it in, or you can write QED, which is quid erat demonstratum. That is Latin for I showed you what I said I was going to show you. Questions at all on verifying this identity? Okay. Oh, also, I don't want to forget to mention, my math lab seems to be back on track. So I did push the due date to, I think, Thursday night, just in case they have a hiccup between now and then. So I did check that out this morning and adjust the homework accordingly. My math lab doesn't, there may be 0 homework problems for verifying trig identities on my math lab because I don't like the way they do it at all. So make sure if you need additional problems that you're pulling up the ebook and doing additional problems yourself. Next, we want to verify sine squared divided by cosine equals secant minus cosine. Well, all our arguments are the same, so I can't identify the more complicated side based off of the argument. The left side's a fraction, the right side's not a fraction. I'd probably start with the left side. It's typically easier to break things down than to build them up. So breaking a fraction down, simplifying it into not a fraction is typically an easier algebra move than trying to build up a fraction. But I want to talk algebraically about what has to happen. So I'm going from a fraction to not a fraction, so that means that something has to simplify. But also notice that we're going from a single term over here on the left to multiple terms on the right. So how does a fraction with just a single term turn into 2 terms that don't have a fraction? What has to happen algebraically for that to be possible? Any ideas? Anybody before I just give it away? Well, the only time that we've gone from fractions with a single term to multiple terms on itself is that our numerator would have to contain multiple terms. Like, I don't know, maybe we had stuff like 4 plus 2i all over 2. And then we break this up into 2 separate fractions and simplify, and you get something like this. Algebraically, that's what has to happen with this one as well. We need the numerator needs to become multiple terms. Then we're going to have to break it up into 2 separate fractions using cosine as our denominator. And then we're going to have to simplify each fraction. So that's kind of our plan. And I really encourage you to try to think about a plan before you just start bulling into these. I think that's where people run into trouble, and then they don't have a clear plan, so they just start doing things and make it worse than what they started with. Well, now we got to figure out, how do we turn that sine squared into multiple terms? Any ideas on what substitution we can put in for sine squared that involves multiple terms?
Substituting 1 plus cosine squared or 1 minus cosine squared. I can't remember.
Yeah, you're so close. 1 minus cosine squared. Recall our Pythagorean identity. Sine squared plus cosine squared equals 1. So I can solve for sine squared and get 1 minus cosine squared. We use this a lot. I mentioned that when we saw our power reducing formula, because people tend to be drawn to the power reducing formula, but it's really this that we use the most. So let's substitute sine squared with 1 minus cosine squared. Here, maybe up. Now we can break it up into multiple fractions using cosine as our denominator. And then we'll simplify each of these. And keep in mind with what we're trying to get to. So I periodically glance up and look at my right-hand side. We know that 1 over cosine is equal to secant. Great, that's our first term on the right-hand side. And then cosine squared divided by cosine is a single cosine, and there's our right-hand side. That's it. Questions on this example? And there can be more on some of the, especially more complicated ones, there can be more than one correct way to verify the identity. So if you have an idea different than my idea, please speak up about that, and let's talk about, sure, that's a great idea, or why that may not be the approach you want to take, because you might make your equation a little more complicated than it needs to. Next, we want to verify that secant to the fourth minus tangent to the fourth divided by secant squared plus tangent squared is equal to secant squared minus tangent squared. Which side would you say is the more complicated side?
Left.
I'd definitely say the left, because the argument's the same for all of them, but on the left, I have higher exponents and I have a fraction. So I would definitely start with my left side. And then I want to think algebraically about what has to happen to go from just the algebra form I have on the left to the algebra form on the right. Every time I write side thoughts, I giggle to myself. I had a hardcore Poindexter math professor, Dr. Wingler, and he always called it the dirty work on the side. I always thought it was hilarious. Okay, so our side thoughts, how do we go from a fraction to not a fraction? Algebraically, what has to happen? Well, we
have to multiply by the reciprocal.
Okay. Not necessarily. So if you were to multiply by the reciprocal, we would automatically get 1. And honestly, it's not a legal math move for us to multiply by the reciprocal, because when you're verifying these identities, you don't work both sides at the same time. So we're starting with one side of the equation and showing that it's equivalent to the other side of the equation. So we can't multiply by the reciprocal unless we're doing that to both sides. And when verifying identities, we don't work both sides. So good idea, but not applicable here. Anybody else have an idea?
Can you just take the secant to the fourth power and divide it by the secant to the second power, and then it just becomes secant squared?
Like these two, just pair them up like this?
Yeah, and then it would just become secant squared minus tangent squared.
All right, so if I have something like this, x squared minus y squared over x squared plus y squared, can we just cancel these x's and these y's out? Is that a legal algebra move?
Well, I mean, would it be dividing the exponents though? The 4, because when you divide the exponents, you just subtract them.
Okay, is that applicable when it looks like this?
I don't know.
I know that damn algebra, right? So if it looked like this, you are exactly correct that we would subtract our exponents, but notice the difference between the two. Here we have multiplication, here we have addition and subtraction. When you have addition and subtraction, the only way that you can simplify is by canceling common factors. When it's multiplication, it's already in factored form, and we can just simplify using our exponent rule. So our left-hand side has addition and subtraction. So I can't just simplify those exponents on secant and tangent. What we're going to have to do is we are going to have to factor the left-hand side, and then we're going to have to cancel common factors. Sometimes it can be tough to do the factoring when you have all of these trig words. So I would encourage you to kind of just strip it down to make the algebra easier. We have s to the fourth minus t to the fourth. How could we go about factoring that?
Isn't it just a difference of squares?
It is the difference of two squares. So what's it going to factor into?
Secant squared minus tangent squared times secant squared plus tangent squared.
You got it. So I'm having real bad notation over here on the side because they're just my side thoughts. That's not part of my proof. So I can have bad notation over there, but I'm going to make sure when we actually write out the proof that we have our good notation. So Josh is right. We're going to start with our left-hand side. Our numerator is going to factor into secant minus tangent times secant plus, I'm sorry, secant squared. Those are all squared. So secant squared minus tangent squared times secant squared plus tangent squared. Now, technically, secant squared minus tangent squared could be factored further. We have the difference of two squares there that we could apply, but keep in mind, you want to periodically glance to the other side of the equation and think about what we're trying to get to. Now that we're in this factored form, we can cancel common factors. So I can cancel this whole thing, secant squared plus squared, and we'll be left with secant squared minus tangent squared, which is indeed our right-hand side. Questions on this example? Al, I will say that I feel like verifying trig identities is one of these topics that you really do need to do a large volume of problems. I frequently say, oh, most of your studying should be studying procedure. Not with trig identities. You have to do a large volume of them to really get it down, because there's a variety of algebra techniques that can show up in the middle of these identities. And if you only practice 10 of them, you're not going to see all the techniques that you need refreshed on. Josh, would you mind muting your mic? Thanks. Until you're ready to talk again, and then that's great. All right, so let's take a look at this one. For the first time, we have an argument other than just theta. Frequently, when I have an argument other than theta, I would start with that side. However, my left-hand side is some binomial squared that would involve writing it twice and foiling it out, and I feel like I wouldn't be able to build up to that. So I think I want to put a variety of side thoughts over here because I don't see it right away, what I should do. Well, on the left-hand side, I see that I have sine minus cosine quantity squared. Since we have a binomial squared, we're going to have to write that twice and FOIL it out. So this turns into sine squared minus 2 sine cosine plus cosine squared. All right, well, I still don't see how that's quite the right-hand side, so let's talk about what the right-hand side looks like. I see that sine of 2 theta in there. What do we know about sine of 2 theta? That's the same as 2 sine cosine. So my right-hand side is 1 minus 2 sine cosine. And I see minus 2 sine cosine up here as well. Is there any way that sine squared plus cosine squared can turn into 1?
That's one of the identities.
That's our Pythagorean identity. So I feel like I kind of have a plan. I mean, do you guys see the plan? We can start with the left-hand side, write it twice, FOIL it out. Then we can substitute 1 in for sine squared plus cosine squared, and sine of 2 theta in for the 2 sine cosine, and we'll have ourselves a proof. You can write all the side thoughts you want, and kind of work both sides a little bit. Can't multiply both sides by the same thing, but work both sides, develop a plan, and then come over and write a nice proof. Some instructors I've seen, they're crazy. They're like, just start on the left and go to the right. Well, what if I don't see it? So I feel it really necessary to put out those side thoughts about what's happening. All right, so starting with our left-hand side. And our good notation now. So sine minus cosine times sine minus cosine. And then we'll multiply this out. Sine squared minus sine cosine minus another sine cosine. Plus cosine squared. Combining our like terms, we're going to get sine squared And I think I'm gonna move the cosine up to the front. So sine squared plus cosine squared minus 2 sine cosines. We already know where we're going here. All right, this is equal to 1. This is equal to sine of 2 theta. We're going to be equal to 1 minus sine of 2 theta. And that is our right-hand side. Questions at all? Okay. Next, we want to verify that sine of alpha plus beta divided by cosine of alpha cosine of beta is equal to tangent of alpha plus tangent of beta. We want to start by determining which is our more complicated side. What do you think? Right, our left side for sure, because not only do we have an argument of alpha plus beta, we have a fraction as well. Similar to one of the other identities we've had today, notice that we're going from a fraction with a single term in the numerator and a single term in the denominator into multiple terms that aren't fractions. So what do we see algebraically that had to happen before? The numerator had to turn into multiple terms. We then broke it up into multiple fractions and then simplified each fraction. That is the algebra that has to happen here as well. And since we're starting on the left with a bunch of sines and cosines and we're ending on the right with a tangent, I bet the second to the last step is that we're going to have sine of alpha over cosine of beta plus sine of, no, I'm sorry, I said that wrong. Sine of alpha over cosine of alpha plus sine of beta over cosine of beta, and then that'll turn into tangent. I feel like that's going to be my second to the last move. So we need to turn this numerator into multiple terms. How could we accomplish that? We know a whole bunch of formulas, so I would definitely be thinking about all the formulas we know. Is there a formula we know for sine of alpha plus beta that turns it into multiple terms? We can use our sine sum formula. This turns our numerator into sine of alpha cosine of beta plus cosine of alpha sine of beta. Now that we have our numerator as multiple terms, we want to break it up into separate fractions, both having a denominator of cosine alpha, cosine beta. Any questions so far? And now we want to simplify each of these fractions. In our first one, cosine betas cancel. In our second one, cosine alphas cancel. So here we have a sine of alpha over cosine of alpha plus sine of beta over cosine of beta. We know that sine over cosine is tangent. So this turns into tangent of alpha plus tangent of beta, and that is our right-hand side. Anybody have any questions so far? Again, so this is frequently a topic that people struggle with, especially the first time they're seeing it. So if you have questions, make sure you're asking. Oh my. Secant minus tangent squared plus 1 divided by secant cosecant minus tangent cosecant is equal to just 2 tangent. We start by identifying which is the more complicated side. What do you think the more complicated side is?
Left.
Definitely the left. So thinking algebraically, what has to happen? Well, a whole bunch of stuff has to cancel. Our denominator has multiple terms in it, and our numerator has multiple terms in it. The only way to simplify a fraction like that is to cancel common factors. So we need to get both the numerator and the denominator in factored form and then try to cancel some factors. I would not switch any of this into sines and cosines because we're starting with tangent and some others, and then we're supposed to be equal to tangent. So I would not bother switching this into sine and cosine. So kind of our algebra thoughts though. Is that we're going to have to factor the left-hand side and then cancel common factors. Is that numerator ready to factor? Can we factor secant minus tangent quantity squared plus 1? And you can try stripping it down. Secant minus tangent squared plus 1. When you look at that, can you factor that? No, we can't. So what we're actually going to have to do is first multiply out the left-hand side numerator. And then it should give us something that we can factor. So we're going to have to write this twice and multiply it out, since we have that minus sign. So let's do that. And then our plus 1 still at the end. Multiplying, we're going to get secant squared minus secant tangent minus another secant tangent plus tangent squared. And we still got that plus 1 tacked on the end. All over our denominator. And it's important that you don't shortcut it here when you're writing out this proof. Yes, it's tedious to keep writing it, but that's what we need to do. Looking at this numerator, I see that we have like terms here. I also feel like secant and tangent and 1, that's got to be some kind of Pythagorean identity, right? Let's see. Remember what they all are. Start with the one I know. I'm going to divide everything by cosine squared. That gives us the Pythagorean identity tangent squared plus 1 equals secant squared. Well, notice what we have right here, tangent squared plus 1. We could substitute a secant squared in for that. So we want to do both those moves. So here's secant squared minus 2 secant tangents plus another secant squared all over our denominator. Still working in the numerator, we actually have like terms. Those 2 secant squareds can be combined. 2 secant squared minus 2 secant tangent. Any questions so far on what we've done or why we've done it? Well, we've already mentioned that we're going to need to factor the left-hand side and then cancel common factors. So we've got everything all multiplied out and simplified as best we can. Oh, can we factor this left-hand side? Let's start with the numerator. Is there anything we can do to factor it? And the continued side work might help. 2s squared minus 2st. Like, what can we do to factor that?
You could factor out the 2.
Anything else?
The s, maybe?
And an s. That's right. So if we factor out at 2s, that leaves us with s minus t. So there's our numerator there. We're going to factor out a 2 secant. And then we're going to be left with secant minus tangent. And then in the denominator, we want to try to factor that as well. And it can be helpful, like I did with the previous one, to kind of strip it down on the side. We've got SC minus TC. Can we do anything to factor that?
We can factor out a cosecant.
You got it. And now that we are in factored form, we can cancel any common factors. So we have secant minus tangent on the top and bottom. Just looking what we're trying to get to tangent. So we're going to be left with 2 secant over cosecant. Well, there's the 2, but I need that secant over cosecant to turn into tangent. So chances are I need to get sine over cosine. So now that I'm here at the end, I'm going to rewrite secant and cosecant in terms of sine and cosine. And like I said, we should end up with sine on the top and cosine on the bottom. Secant is 1 over cosine. I think I'm just going to leave this 2 out in front because I know that that's good and I'm looking for that. So 1 over cosine. And then cosecant is 1 over sine. This becomes 1 over cosine times sine over 1. That is going to be sine over cosine, which gives us 2 tangent. There's our right-hand side. Sorry. That one was a little bit longer. I think it was a lot of rewriting. But questions at all on that one? Or strategy? Okay. Oh, before I get to this next one, I wanted to mention that I did set office hours. I posted them in D2L as a result of the survey. So I'm going to have office hours on Tuesdays and Thursdays right before class from 10:30 till 11. And then I'm going to do Monday nights for you guys at 6 o'clock, 6 to 6:30. So there's an evening. And I can do by appointment as well if none of those work out for you, or if you just need something quick before the next office hours roll around. But I did post them on D2L so that you can see them there. Next, we want to verify that sine of x plus sine of 3x equals cosine of x plus cosine of 3x, that is equal to tangent of 2x. Oh, anybody have any thoughts? Because I think these identities are, I don't want to say easy to follow when somebody's directing you, but when you look at it on your own, that's where it can be hard to get started. So now that I've done a half dozen, what kind of ideas do you guys have for this?
Well, sine over cosine is tangent, but I don't see how you would get it to 2x.
Okay, so I like your idea, though, that you think that our second to the last step is that we'd have to have sine of 2x over cosine of 2x to turn it into tangent of 2x. I totally agree with that.
Might be pointless, but can we just split them into two different fractions?
Like this, over a plus sign?
Yeah,
Absolutely not. All right, can't do it with a plus or a minus sign, only when it is multiplication or division. I know, it's so tempting, right? But can't do it with the addition or subtraction. And then it's weird, like, look at that, on our fraction, we have multiple terms, and we're trying to get those multiple terms to a single term, because we probably are gonna end up with sine of 2x over cosine of 2x. So do we have any kind of formula that turns multiple terms that are being added together into a single term? And a single term just means that it's not separated by addition or subtraction.
Could we use the sum to product formulas?
Let's try that. If we use the sum to product formula, sine of x plus sine of 3x would turn into 2 sine of, what, add them together, divide by 2, 2x. Hey, that looks promising. And then cosine of negative x. Well, well, at least that gave us a 2x. That looks promising. Let's try that. So starting with the left-hand side, doing a sum to product formula on the top, that's going to be 2 sine of, right, a plus b over 2. So that's x plus 3x over 2. And then cosine of x minus 3x over 2. And then on the bottom, we'll use our cosine sum formula. This becomes 2 cosine of x plus 3x over 2, and then cosine of x minus 3x over 2. Suggestions on what we should do with this?
What formula did you use for the top?
The top sum to product identity. Sine of a plus sine of b equals 2 sine of a plus b over 2 cosine of a minus b over 2.
Okay.
So we could just, straight clean this up. Sine of, that's going to be 4x over 2 is 2x. And then this is going to be cosine, that's negative 2x over 2, that's negative x. And then on the bottom, same thing, cosine of 2x, cosine of negative x. And we're trying to get to tangent of 2x, which is likely going to look like sine of 2x over cosine of 2x. Are we getting close? What can we do at this point?
Can you get rid of cosine negative x?
All right, why can we do that here, but we weren't able to do it here? What's the difference?
Multiplied.
Right, see, now we're in factored form, so we can cancel things. We couldn't do that from the beginning because we were not in factored form. So we can cancel out the cosine of negative x's. Anything else?
Could you also cancel out the 2's?
You got it, canceling out the 2's, so we're left with just sine of 2x over cosine of 2x, and there's our tangent of 2x. There we go. questions at all? So when I was making my videos, I realized that I had a duplicate. So we already did this one. Next, we want to show that secant of 3 pi over 2 minus x is equal to negative cosecant of x. Which side do you think is the more complicated side that we should start with?
Left.
I agree. And please know it is it's not always the left-hand side. I know a bunch of them here are the left-hand side, but it's not always the left-hand side. All right, so I got to get from an argument of a 3 pi over 2 minus x to just an argument of x. Ideas on what we can do here? Well, in hell, I don't have any formulas for secant and cosecant, do we?
Should we put it in terms of cosine?
I would rewrite it in terms of cosine because I have no formulas for secant. I guess that's the first thing we're gonna have to do. This is 1 over cosine of 3 pi over 2 minus x. So I guess that means that ultimately we're trying to get to on the right-hand side going to be negative 1 over sine, I guess is what we're kind of planning that we're getting to. Okay, suggestions on what we should do with that cosine of 3 pi over 2 minus x.
Can we use the co-function identities?
Okay, so how do you see the co-function identity helping you?
There was just an example that looks kind of like it.
Okay, so let's think about that over on the side. Let's see. So our co-function identity would say that cosine of 3 pi over 2 minus x is going to be equal to sine of 90 minus that argument. Oh, I shouldn't even put 90, right? I guess I should put pi since we're in radian, or pi over 2 for that matter. Okay, so that would be sine of distributing my negative. Pi over 2 minus 3 pi over 2 is a negative pi. And then plus x. And we're trying to get to negative 1 divided by sine of x. So we know with fractions, the negative can be top, bottom, or out in front. So I guess we could put the negative down here with the sign. I'm trying to turn that then into negative sine. If we use our co-function identity, now what? And you have not led us down a terrible path, so we can still build off of this. We have an argument that is a sum, and we need the argument to not be a sum. The formulas that we have for that are sum and difference formulas. So we could use a sine sum formula here. So Riley, what you suggested is not wrong in any means, but I'd feel like it did add some extra steps. We could just go right to our cosine difference formula. If we did this extra step and then did our sine sum formula, we're still going to get exactly the same answer. So you didn't lead us down a wrong path, but I think this path has a few extra steps here that we could avoid. Again, not wrong. There's frequently multiple ways to do it. Either way, whether we're looking at this or we're looking at this, we're going to have to use a sum or a difference formula. But if it's okay with you, I'm just going to use our cosine difference formula, which says
Yeah,
that
that's fine. Sorry about that.
No. These are good ideas. You know, this is what I'm trying to train your mind to do. I love these ideas. This is what we're looking for. And sometimes I even run with terrible ideas just so that we see, because that's going to happen. You're going to be working on these identities on your own. You're going to try stuff that seems right, and it's either going to work out or you're going to be like, oh no, I got to try something different. So it's all part of the learning process. I like all the ideas. That's why I asked for them. All right, so our cosine difference formula says cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. So we get cosine of 3 pi over 2 times cosine of x plus sine of 3 pi over 2 times sine of x. So let's think about what is cosine of 3 pi over 2. So 3 pi over 2 is down here. Our cosine value is 0. So this becomes 0, and when we times 0 by anything, it wipes it out for us. And then sine of 3 pi over 2 down there is -1. So we're going to have 1 over, we don't even need to write that 0, -1 sine of x. Hey, there's our negative cosecant. And there we go. I'm just going to do it out here over here on the side with what Riley had suggested, just to show you guys we're going to get exactly the same answer. All right, so here we get sine of negative pi cosine x, sine of x cosine of negative pi. Man, I almost feel like it would have been easier if I flip-flopped this argument so I didn't have all these negatives, but I'm just going to go with what I have. Sine of negative pi, using our negative angle identity, this is negative sine of pi. And cosine of negative pi, well, that's the same as just cosine of pi. All right, so let's plug in. I'm going to figure out what sine of pi is. So pi is over here. Our sine value is 0, so that wipes this whole thing. And our cosine value at pi is -1. So we still end up with that negative sine of x. So that would have totally worked as well, just had a couple extra steps. Questions, anybody? All right, well, let's do one last one. Oh, geez. Because all I had to do for the whole week is these identities. Do you guys want to just stop now so that we have 3 to do on Thursday? Give you guys some time to practice some out of the book, get caught up on that homework that wasn't working yesterday? Now that I see that there's only 3 more.
Works for me.
That sound okay to everybody? Again, to give you guys
I'm okay with
12
that.
minutes here that you can work on your homework that wasn't working yesterday. Questions on anything, anybody?
I do have a question from the homework, if that's
Yeah,
okay.
sure.
I'd have to pull it up here, but it was like the last one of the homework. It would end up getting really complicated where the sign of like S and sign of T would both have square roots in them, and then for some reason I kept messing that up.
Okay,
when-
sure. You can just pull it up and you should be able to share your screen.
Okay.
We can all look at it together. Although I did get an email about like locking down our share screens. Apparently, Zoom bombing is something where people who are not like you guys, just like some random person, if you leave your Zoom as public, can take a hold of your screen, and then they're putting like all kinds of pornography up in the middle of people teaching their class. So please know if that ever happens, it's certainly not me. And I'm gonna adjust a setting. I'm probably gonna cancel the whole meeting and then get back.
Host disabled participant screen.
Oh, maybe I
share.
already did that. So nobody's
I'm not gonna put porn on the screen, I
Yeah, please.
promise.
Okay, hold on here. I think I can. Okay. Oh God, I'm putting all participants. So here we go. All right, go ahead. Try now.
All right. Is it this one? Is
Yep.
it working?
Yep.
Okay. Yeah, this, I'll do like a similar question.
Holy moly.
But for some reason, I cannot get this question right.
Okay, so there is one exactly like this in your notes. All right, I'm gonna write this stuff down because this is not a short problem.
I saw the one in the notes. Like, there's a million problems just like this in the homework. It's just this particular
Just
problem.
this one.
Yeah.
Okay, both parts or?
I think it's actually when we get to tangent is usually where I can't get it. Because I get
Okay,
the
so-
quadrant and sine, but not tangent.
Yeah, things get crazy once you get to tangent in this problem, or like the problem similar to this one, because it's like square root of like minus the square root, like square root of 6 minus the square root of like 5.
Okay, all right, I'll do it.
Sine
Stop
of
sharing your
2.
screen. I wrote it
Okay.
down, so stop sharing your screen and I'll do the tangent of S plus T. No, wait, I didn't share my screen again. So for tangent of S plus T, our formula says that this is tangent of S plus tangent of B over 1 minus tangent S times tangent of B. All right, so I'm going to make a couple triangles here with the information that was given. Oh, what quadrant did it say S was in T? I didn't write that part down.
Quadrant 2.
S is in quadrant 2. Okay. So opposite hypotenuse, this is going to be the square root of 48, which is 4 square root of 3 down here. And how about quadrant, sorry, what quadrant is angle T in?
4.
So 49 minus 36 is square root of 13 over here. So tangent of S is going to be, forget that's negative, tangent of S is going to be 1 over 4 square root of 3 plus tangent of T is negative 6 over square root of 13, and then in the bottom, 1 minus this product. So what I would do to simplify this gross complex fraction, first I'm going to take care of some signs because I got too many signs going on. So I'm just going to make this minus up top and just plus in the bottom. To simplify a complex fraction, you want to multiply each individual term by the LCD of all the fractions. And our LCD this time is going to be 4 square root of 3 times square root of 13. So I'm going to multiply every single one of these fractions by that. And I could make that square root of 39. I'm just not because I want to be able to cancel stuff and it'll be easier for me if I can just see it. So 4 square root of 3's cancel, square root of 13 cancel. Everything cancels, nothing cancels. So that's giving us square root of 13 minus 24 square root of 3 all over, now I am going to make this 39, 4 square root of 39 plus 6. We okay to there? And now we just need to rationalize it. So we'll multiply by the conjugate.
Where did the 39 come from? I missed that.
Right here, when I multiplied the square root of 3 times the square root of 13, that's where we're going to multiply insides together and leave it on the inside.
Thank you.
Oh, this is going to be gross. I don't even have a calculator. Okay. All right, so that's going to give us a 4 on the outside. $13 times 39, that's going to be square root of 507. Which actually, by the way, which will simplify, this is going to be 169, square root of 169 times square root of 3. So this will simplify down to 13 square root of 3, that radical. And minus 6 square root of 13. Then minus -96 times the square root of 117, and that simplifies as well. That's the square root of 9 times the square root of 13. So we'll get 3 square root of 13 there. And then plus 144 square root of 3. And then in the denominator, we have conjugates, so we only need to multiply the first two together. And then the last two together. The first two, multiplying them together, that'll be 16 on the outside and then a 39 without the radical. And then minus 36. So this numerator, we have 4 times 13 square root of 3. So that's going to be 52 square root of 3 minus 6 square root of 13. Now we've got 96 times 3 square root of 13. That is minus 288 square roots of 13 plus 144 square root of 13. Multiplying and subtracting our denominator, we're going to get 588. We doing okay so far? Ooh, I feel like I'm missing something. Okay, this is 288 square root of 13. Okay, so these two go together. That's going to give us 196 square root of 3. Minus 282 over 588. And then I'd break these up into 2 separate fractions and then simplify whatever's on the outside. That has to simplify by something. At least 2. And then that should be your answer.
What happened to the square root of 13?
Oh, I just didn't write it. Sorry. That's what the hell did, and actually that's not even 288. Jeez, oh man, I missed a negative. All right, so it's negative 6. Sorry. Minus 288. So this is a negative 294 square root of 13. There it is. And then simplify what you have on the outside, and that should take care of it. But I think it's this middle part here where you're dealing with this complex fraction here that's extra tricky. And it can be much more direct, just multiplying through by the LCD, and then having to FOIL out just these more complicated here in the middle. I think that's tricky too. So try the next one, and if you run into trouble, just shoot me an email and then I can take a look at it again. Send me a picture of your work if you're going to choose to do that, because then I can pick out where you're having trouble. Anything else?
No, I think we're good.
All right, I will see everybody on Thursday.
Goodbye, Mrs. Kraft.
Bye.